thank you to Sydney for pointing out my muting. This online teaching and muting issues have come back to get me again. Anyway, where I started out is, congrats on a great job on the exam. Everyone did very well on exam one. 95.6 was the average, which is comfortably in an A. Obviously, that's fantastic, and I couldn't be happier that most folks are well in line to get an A after the first exam. It's actually a little bit better performance based upon prior experience in previous years, but that's totally fine with me. I apologize for the rubric troubles. All the exams were right on the screen, but for some reason it wasn't accepting any answers for two of the questions. But I was able to get that sorted out, so everyone did get the points for those questions. If you have any questions about anything you had wrong, please let me know, and I can go over that with you. Send me an email. But in general, I think there's nothing more to say about the exams other than fantastic, good job. You'll probably have noted, I'm sure you're just excited to get back to doing worksheets bright and early Monday morning, but there's actually not a new worksheet this week after the exam and the worksheet that was due to help prepare you for the exam. Last week, I decided to give everybody a little bit of a week off since we're especially still going on with seismic, related seismology and earthquake related discussions. So you didn't miss anything. There's no new worksheet, and don't worry, we will get started again next week on that. More broadly, I hope everyone continues to do just as well for the exam, but if you feel comfortable with the preparation, doing the worksheets, studying the review sheets, and how you did in the first exam, I think you'll be perfectly fine the rest of the semester. There's exams 2 and 3 are coming, but they'll be very much similar style to that one, and hopefully that won't become too much more stressful as we move along. So with that being said, I don't think there's any more reason to discuss the exams. If you have any questions, send me an email or just let me know, and I'll look into any problems related to the exams. So really where we left off on the lecturing portion of the class was talking about earthquakes. And just to remind you, I won't cover this in great detail again, but we're going to talk about the 3 types of seismic waves. You all are experts on this now after having completed the exam dealing with this and doing a very good job. The key thing to remember here is the 3 types of waves are P waves, S waves, and R waves. P waves are compressional waves. Compressional being the energy is transmitted, like you can think of hitting a spring and having it sort of push out and then pull back in. And those P waves, I won't show you the video again, are the fastest moving with the most energy. The S waves the P waves can travel through liquid, solid, or gas. S waves can only travel through solid materials. They're slower than P waves, have less energy. I remember the difference is these are more up and down waves, like you think about the waves in the ocean, for example. And then R waves are what we call surface waves. And the key thing to remember here is there's no clear pattern. They're very complex, depends upon a lot of factors. They travel a lot more slowly with longer frequencies. We'll talk about what that means in a second. But the key thing I want to say here is that except for the area very close to the epicenter, so above the focal point of the earthquake, almost all the damage outside of that small area is actually going to be done by these R waves. These can be incredibly damaging, largely due to their chaotic nature and unpredictable nature. So most of the damage we're going to talk about with earthquakes, and certainly the big earthquake hazards have actually been tied to damage from R waves. So remember, these can kind of be rolling and create these sort of counter balanced waves that go in the opposite of the direction of propagation. So what we're talking about here again is that as the S waves travels along, the R waves in kind of this sort of semicircular rollback beneath them, which is really complex, creates a lot of damage for buildings. So the key thing here is that an ideal seismograph here is that what we're going to think about is that when you're in a given location from at a certain distance from an earthquake, what happens, you'll have a normal background level of what's called microseismicity, or this is actually a combination of micro tremors on the earth and or the reliability of your instrument sensing will sort of have a constant background. And what you'll see at some point in time is that there is a P wave that will arrive. And the key metric that most seismologists are going to be interested in is actually, or the key metrics that most seismologists are going to be interested in is the amplitude of these seismic waveforms, and the travel time, or the amount of time that elapses between the P and the S waves arrival. And that time frame based upon knowing the rate at which P and S waves will travel, can be used to calculate the distance of the earthquake epicenter from where you're at. So, for example, you wouldn't be asked to calculate this, but something that traveled 50-second time gap, traveled to a local seismograph, and at a 50-second time gap between the P and the S waves would indicate about 420 kilometers, and you can scale that accordingly. And of course, the actual time gap between the S and R waves sort of falls same plan, but the R waves, because they're not as predictable in terms of the wave energy, they're not really used for anything relevant to that. But the other aspect, in addition to the timing of the different waves arriving, is the amplitude, which actually allows you to determine the amount of energy that was released from an earthquake event. So, for example, this is a real example of something called SCEC, which is Southern California Earthquake Monitoring Center. And because of the immense seismic hazards that are present in California, particularly in Southern California, there are seismic stations all around the area. There's actually more even been added since this map's been made, I'm sure. And what they can do is pretty reliably, almost instantaneously, that data comes off of the seismographs into a central network where they can actually locate the focal point, the epicenter of an earthquake, and get a sense of the magnitude and things like that. I mean, at some level, you can be skeptical and say, what's this going to do to help us mitigate a hazard? It really doesn't, but it does allow you to sort of be prepared to understand what you're dealing with and make some predictions as to what kind of buildings need to be inspected, what kind of infrastructure like pipelines and roads need to be inspected, because as we'll talk about in a minute here, each of them can be affected differently by different earthquakes depending on their energy output or their magnitude, and as well as their depth, how far the focal point is below the epicenter. So a perfect example, obviously the travel time the time elapsed between the P and the S wave would be much less here than it would be out here. And basically the way you can do this is you need at least 3 seismic stations to triangulate. Then have one here, here, and here, for example. You can triangulate based upon drawing a circle of a fixed amount of time around an area to determine where that earthquake actually would have occurred. Obviously, in this example, there's so many more you can determine it really precisely. But on a global scale, it's usually done by knowing the travel time, the gap between the P and S wave, associating that with a distance, then taking in the old days, we actually took compasses and drew circles around those points and saw where they intersected to determine where the earthquake occurred. So, the key thing here is that the time of arrival and the amplitude, are the key aspects here. The time of arrival, shaking will start to increase once the P wave gets there. It's not going to be enough time to actually say something about predicting hazards, but the amplitude will start to decrease now once we see the R waves coming through, where most of the damage occurs. So, just to think about this, there's some key terminology around these waves. The easiest way to think about the frequency and then the amplitude of the wave is imagine standing on a pier and watching the ocean waves, come rolling up the shore. If you watch one wave, the next wave, and you counted the amount of time that elapsed between each of those waves, you can think of that as the wave period. So if it's one wave every second, which would be pretty fast, that the wave period would be 1 second. The example I use here for discussion is that if you have if a passing wave, each passing wave is 1 cycle, and if a wave passes you every 10 seconds, then the wave period is 10 seconds. Okay, and then the frequency is basically the inverse, or 1 over the wave period. So, for example, if you want to calculate the frequency of a given wave, it's always done in per seconds, and 1 per wave period, or 1 every 10 would be a frequency of 0.1 hertz is the unit used to determine the frequency of something. So you can all divide this on your own, but if you had a wave period of 1 second instead of 10 seconds, that'd be 1 divided by 1, which means 1 hertz. So the key aspect here is the less time elapsed between successive waves, the higher the frequency is going to become. And again, those frequency units are going to be in hertz. So for perspective, most P and S waves have frequencies that depending on the amount of energy that's released and the type of rocks vary between about 0.5 to 20 hertz, with the S waves, of course, being slower by about a factor of 2 compared to that P wave. But this is the range we're talking about. Um, so surface waves, again, lower frequencies. That means a longer wave period, and these are often, less than 1 hertz or less than 1 wave per second. So, key aspects here, of course, we already talked about this a bit. During an earthquake, both high and low frequency waves will be generated. Um, when you're, as I alluded to already, if you're near the epicenter or above the focal point of where that earthquake intersects the surface, all of the waves can do a lot of damage. And the high frequency waves particularly can do a lot of damage and will often damage low buildings. It's because if you think about the surface of the earth having a very low building, all that energy gets dissipated in the actual building itself. So low buildings can often see a lot of damage local to the epicenter or just above the epicenter, because of high energy waves. But more broadly speaking, the low frequency waves, which can be both local to the epicenter or spread out across the surface, are often the ones that can do the most damage and do particularly damage to the tall buildings. So you think about the low buildings, you get a really high frequency wave, dissipates a lot of energy very quickly. The taller buildings, the slow moving waves actually can cause the building to sort of heave and haw, which can do a lot of damage both near the epicenter and around that area, or even with pretty great distance around that area. So key aspects here is with increasing distance from the epicenter, high frequency waves are pretty quickly attenuated. So the P and the S waves, even though the P wave can go through solid, liquid, and gas, the rate of transport, the wave frequency, can actually be affected by something called attenuation. So going from solid to liquid to solid to liquid to solid to liquid can actually cause the wave to slow down through each successive step. And as a result, the really high frequency waves can kind of get disbanded and lost pretty quickly if you go to areas far away from the epicenter. So basically, areas near the epicenter can often feel the rapid shaking. But if you move away from that epicenter, you feel that there's less and less effects. And often, even in relatively large magnitude earthquakes, 30, 40 kilometers from the earthquake, the extent to which people feel those P and S wave can be really, really minimized. Key thing here is that the lower frequency waves, the R waves, can travel extremely long distances, and in fact can actually damage particularly tall buildings really far from the epicenter. Hundreds to even 1,000 kilometers is not an irrelevant discussion here. We talked about earlier in this lecture before the exam about the earthquakes in the New Madrid Fault along the Mississippi River in Missouri, ringing church bells in Boston, and really it's these low frequency R waves that were actually causing the bell to ring that far away, although to a very lesser extent there was actually some P wave and S waves that we felt in that area. So the other factor you really need to consider when you're thinking about building a house or designing a city, putting a set of buildings in a location is actually the material amplification. So, and then we're talking here about both how we're going to design a sustainable infrastructure, bridges, dams along rivers for reservoirs are another important example, and more commonly buildings. So these can be schools or residential apartment complexes, or they could just be houses. But the key thing to remember here is that different materials will respond differently to different waveforms and different degrees of energy. So I'm going to just ask for a very quick thought on this, but consider if you have something made of cement, which once it's solidified is very rigid and brittle and prone to breaking, but not very ductile, versus a building constructed out of wood, for example, where it can sort of heave and haw a little bit. It may not be as affected in the same level. So which do you think is going to be more likely to be affected by or damaged during a given seismic event? Something made of wood or something made of cement? So I got a good guess here that more brittle material, such as cement, will be damaged more, and that's exactly right. And then more ductile material, like wood or composites, has more ductile capacity to sort of bend but not break. That's a very generalized statement, of course, and obviously not everything. You can't build a 100-story high-rise out of wood. But what you do see is that effectively the local code and the local building requirements, for example, what's actually built in places like Los Angeles, for example, you don't see a great number of 100-story buildings like you see in Chicago or in New York, for example. They often tend to have lower lying buildings because of that potential for damage, and most of the codes do that. But obviously, it's not possible to build everything out of cement. So, for example, they often put the buildings on casters where the pylons can actually move on a plane, where they're fixed in place. They can't go too far, but they can move a little bit, so they don't they can bend and not break. And there's been a lot of adaptations in terms of building mechanisms to allow cement to be used, but create preferential areas where it can flex, where it won't break. But in general, the building materials are a really important concept in building something that's going to be robust. For example, you don't see a lot of brick houses on cement foundations in the Los Angeles area, but you do more commonly see those, of course, in the Midwest and areas where they're not going to be damaged by those processes. Not that we don't have plenty of wood houses here. The second factor here is the actual geological materials, and the geological materials also respond quite differently to seismic shaking. So it's not at all a different process, although what's more relevant to geological materials is how easily the waves can be transmitted through the formations. So I'll make it probably overly simplified here a bit, but really hard igneous rocks or metamorphic rocks tend to be very dense. They tend to have minerals that are very closely packed together. And there's two important implications of these types of rocks when it comes to thinking about earthquakes. The first is these dense minerals that are closely packed together can transmit the waves much quicker. Okay, so you can imagine a P wave traveling faster through a hard igneous rock compared to a sedimentary rock such as a sandstone or alluvium or silt, which we'll talk about what that means in a second, if those are new words for some of you. So in general, P waves, S waves, and R waves are always going to travel faster through igneous rocks than they are through poorly sorted sedimentary rocks. The other factor, however, though, is that in addition to the rate which is going to transmit it through, the actual amplitude or the amount of surface shaking you observe, particularly in those R waves, is also a function of those materials. So if you think about holding a piece of cement or a brick or a 2x4 and tapping it on one side, the brick sort of moves, but that's sort of the end of the story. Or if you think about a bowl of Jello, if you hit that bowl of Jello, it'll kind of wiggle around a bit, right? And it's a very similar scenario from going from hard igneous rocks to sedimentary rocks, alluvium and silt, which it can cause much more amplitude of the surface waves if you're hitting a Jello or pudding or something like that that's sort of not very well solidified. So the important thing here is that if you're considering living in California, or if you're considering living along the Mississippi River, down in Missouri, whether your house is actually going to have a foundation built in hard igneous rocks, softer sedimentary rocks, or even alluvium or silty mud rocks, that can have major implications to whether you're going to actually see the house being broken, damaged, or even wiped out by one of these events, even of a similar magnitude. So there are plenty of examples throughout geological history in the last few hundred years where people can actually map what kind of or document what type of rock form is under rock units are under a house or under a building, and whether those actually experience damage or not. So I guess the key thing to consider here is that the solid rocks again are dense. There's not a lot of what we call porosity or space between the grains or the minerals in those rocks. And as a result, there's not a lot of water or other fluids like oil or gas in those spaces. As a result, easy to transmit through it, and not very large amplitude waves when the waveforms migrate through it. As you go into sedimentary rocks, of course, are deposited by wind or by water. They're usually looked at grains that got broken, small grains that get broken off from igneous or metamorphic rocks, and they get deposited. When they do that, they sort of just are imagine taking a box of Legos or marbles and dumping them into a bin. There's a lot of space between the grains, and that space between the grains is a point of weakness. It can be filled with fluids like water or gas or oil. And as a result, when you hit that, there's more stuff that can actually move around and amplify those waves for you. And then coming back to it, alluvium is almost the extreme end member of that sedimentary rock, where you can see really fine grained alluvium. You can think of it as a riverine or lake deposits of really fine grained, kind of muddy material that's not often very well lithified or solidified to rock, and that can just further amplify the amount of damage from surface waves. And then silt is just really fine grained aspects of that. This is usually what you see being deposited in low energy river environments. So it's just an end member. You can think of these three components as having more water and less lithified rock and more water filled space, porosity between them. So, trying to tie these things together, if you think about this major earthquake in the early 1800s in Missouri, if you look around the area near the Mississippi River, in a lot of valleys, you often get these valleys that are filled with sediments and alluvium and sort of riverine deposits. So in that valley, the amount of surface amplitude can be catastrophically large. Okay, but up here on this solidified rock, you're actually talking about sedimentary rocks, and to the east of that, igneous rocks that really weren't damaged very much. So in that scenario, we love to tell the story. It's illustrative of the scale of earthquakes and their influence. Talk about an earthquake in Missouri ringing church bells in Boston. But the key thing here is that, in between those two areas, there's a lot of igneous rock and very dense, deeply buried sedimentary rock where the waves are transmitted through very easily. And even though the church bells rang in Boston, there really wasn't a lot of damage, but that's where you actually go to Boston along the coast. You start getting into sort of alluvium and silt along the margins of the coast, where the sediments can really amplify those waves. And as a result, that's why you hear the church bells ringing there, but we never talk about church bells ringing in Pittsburgh, for example. It's because the amplitude increased once we got to this different type of geological materials. So brings us to one of these themes we'll talk about a lot throughout the semester. Kind of goes back to the idea of sustainability, but the key point here is that the underlying geology, whether we're going to talk about this in earthquakes, we're going to talk about this in volcanism, we're certainly going to talk about this in flooding, and many other aspects of the rest of the course, that the sustainability of what we do often has a lot of implications for the type of materials we use to build. But that's most of the materials we use to build a building are probably most relevant when we talk about earthquake hazards. The second half of this, the geological materials underfoot, the geological materials under the surface that we have to consider in terms of how much damage can occur. Whether it's earthquakes or floods, it often becomes a really important aspect. And as a result, one of my sort of pet hobbies is people, my friends are buying houses. They always sort of ask, is there anything I need to know about this area? And most times there isn't, but in areas that are prone to earthquakes, particularly if you're in one of these areas where you collect, little valleys where you collect alluvium or there's sedimentary rocks, you can have more damage from earthquakes if the area is prone to earthquakes in the first place. So, perfect example of this, we're going to talk about a really large earthquake that occurred in 1985 in Mexico City. That's a bit of a misnomer. The earthquake actually occurred off in the Pacific Ocean. But what happened is that the Mexico City was quite far from the actual site of the earthquake, but there were low frequency waves were transmitted through metamorphic and igneous rocks, and then until they got to this valley bottom in Mexico City that had a lot of the alluvium and sedimentary units we just talked about. And what that did is that actually increased the shaking amplitude by a great degree. All its energy is quickly transported through and then hit sort of the, I'm going to use the example of Jello, but hit the part that we could easily shake, and the amount of damage was pretty catastrophic. This caused the intense transmission of the R waves in that area, caused the shaking to sort of literally rattle the buildings back and forth in a very chaotic way, and eventually led to most of the buildings collapsing. So, for perspective, this earthquake, this earthquake actually occurred off the west coast of Mexico and was transmitted through these volcanic rocks at a very rapid rate. There's a P and S and R was all transmitted in the sort of best case scenario of easily going through this hard igneous component. And then once you actually get into Mexico City, if you've never been there or haven't looked on a map, it's actually in this little valley bottom. I won't test you on this terminology by any means, but it's called the graben. It's where the earth starts pulling apart in a divergent plate boundary, and a little portion of the crust actually sort of falls in upon itself, and that becomes the graben, and that graben's below the surrounding material around it. So anytime there's a river or wind or something like that carries material, erodes it from the surrounding high points, it sort of fills the valley bottom, with sedimentary units, alluvium, that can kind of be poorly sorted, have a lot of space for water, and not really well lithified by geological pressure. And that's an extreme scenario here in Mexico City. So first of all, this graben or valley bottom has been getting filled with wind and water-driven erosion for a long time. But during various aspects of climate change, the area actually filled with a relatively large lake. You can see highlighted here in yellow, where there basically is a lake deposits in the bottom of this. They put really thick sequences of poorly sorted alluvium, which basically is unlithified. That's what differentiates alluvium from sedimentary rock, is that it doesn't get heated up with enough pressure and temperature to actually become a solid form of rock. And as a result, you have this thick package of really, really poorly sorted alluvium that can be, when an R wave strikes, it can do a lot of damage. So for perspective, this is the area of Mexico City built right along the margin of the volcanic deposits, along the margin of the graben. This whole area, again, is within this thick sequence of ancient lake alluvium in the area. And if you weren't, I don't think any of you would have been alive for this earthquake, but I was, and it was a horrifying imagery on the news. But we're talking about almost total devastation of buildings where they shook around to the point that didn't matter; they just all collapsed on themselves. And the death toll was exceedingly high. I don't remember the number of people that were dead, but it was in the one of the biggest natural disasters in North America in the last few hundred years. Similar problems, and this idea, though Mexico City case is the worst example of this. This idea of valley bottoms near volcanic areas being susceptible to near volcanic and plate boundaries being susceptible to seismic hazards is not a new one. This come up in volcanic hazards as well. But remember, we talked about divergent, convergent, and transform boundaries. It's along those plate boundaries where there's a lot of volcanism, where there's a lot of mountain building, there's a lot of seismic activity. And it's also where you see those occurring. You often see valleys and ridges. And those low-lying areas tend to fill very shallow sediments with sedimentary type grains, which often aren't lithified. And as a result, this pattern, when you think about sustainability, repeats itself again and again and again. That the folks living in these alluvium-filled valley bottoms are often at the greatest risk of earthquakes. So you can think about that from a social, environmental justice or social justice scenario too. It's often that the less desirable land is at the valley bottoms. People come to realize this and often avoid these sort of areas where these low-lying alluvium-filled areas where there is great seismic hazards. So it's actually very similar. As I mentioned, this is not uncommon. Very similar for the 1989 Loma Prieto earthquake in the Bay Area. The Bay Area, first of all, it was a human-engineered scenario where there's bay-filled mud, where they took our garbage and debris and actually extended the land surface in the Bay Area to kind of increase the area to do things like have real estate and maximize the quality of the ports for bringing goods in and out. But the area in this valley was also filled with alluvium. So the bedrock is outside of the San Andreas and the Hayward Fault, and within there you have a lot of alluvium and poorly sorted rocks filled with water that are really susceptible to influence by these R waves. So, if you were going to look at the roads up here, no damage whatsoever, but down in the valley bottom, near Oakland, near San Francisco, these are areas where you saw to maximize the amount of damage from R waves, and you saw bridges, buildings, etc. Actually collapsing. And I think it was 41 people were killed in the collapse on the Nimitz freeway alone. So these can be again an area 5 kilometers from the epicenter, no damage, but the areas in this alluvium pretty extensive damage from the fact that the areas that were built on alluvium were just experienced much more damage from R waves. So here it gives you an aerial photo image of that some of that damage, and you can see that there's little undulations where this is it's not just the one piece that actually fell off the caster and fell down. It's actually that you see this damage along most of that Nimitz freeway, and the entire thing basically had to be rebuilt. And of course, we get better at building these, make them more we use building materials that are better suited for withstanding that shaking. But the reality is, when you're fighting Mother Nature, it's a pretty bleak outcome. So, for perspective, Loma Prieta earthquake struck on the 17th of 1989, October 17th, 1989. It was all related to the slip on the Andreas Fault. It was a pretty large earthquake. So the reality is, it's not clear we can really build materials that can withstand a 6.9 magnitude earthquake anyway. We'll get better at it all the time, but most of the things there are about building a ecosystem that's sustainable, where we can find, mitigate disaster relief and get help to people quickly, rather than worrying about trying to prevent damage. It's often not feasible once you get particularly high earthquakes in this. And it killed 63 people, 41 on the Nimitz Freeway alone, and injured about 3,750 individuals. So it was a this is relatively recent, 1989, relatively serious earthquake. Clearly, this magnitude in that area, the early 19th century, I think it was like 1906, 1908, similar magnitude earthquake, and that's expected to be happening, not imminently necessarily, but it's expected that sort of magnitude of earthquake will be not uncommon in that area. So again, the majority of the deaths were actually along the freeway. Luckily, if any of you, it's before all of your lifetimes, I believe, probably, but luckily the freeway is actually less busy, because there was a Bay Area World Series baseball, baseball World Series that was being played between two teams in Oakland and San Francisco. It was just about to start, and as a result, most people were in bars or at home watching games, and there were less people in the freeway than there would have been otherwise. If it happened during rush hour, it would have been a much more devastating loss. So this is to give you a sense of the shaking intensity. Reality is that we show this damage over here in Oakland and in San Francisco, but actually the shaking intensities were even larger outside of the areas. It just wasn't as much damage because of the fact those were solid lithified rocks that weren't gonna have the same amplitude of shaking, even though more energy was actually dissipated, towards Santa Cruz than down in the Bay Area. This was the area where the damage occurred because of the fact that that's where the alluvium was. So important things to think about here. Where do we have large cities, right? Do we tend to have large cities in areas where we can build and control, things like roads and pipelines and communications. It's a lot easier to build a city on relatively flat alluvium, where you can dig the rock material with a shovel or any industrial bulldozer, something like that, than it is in the mountains, where the surface area is going to change a lot. But as a result, you often find that there's really high property values out in these sort of high standing solidified areas. But the reality is that most dense population centers often tend to be in these valley bottoms and alluvium. So a good examples of this is everything along what's called the Western Cordillera in the Western United States. So Salt Lake City, Phoenix, Albuquerque, those are all built along the sort of alluvium right down to Mexico City. All are relatively susceptible. If you wanted to think about this in terms of New York City or Boston, we're all built on coastal alluvium. So in essence, you're sort of left hoping that we don't have earthquakes that bring a lot of our ways to those areas, because a lot of our major urban areas, not just in the United States, I use those as examples, but globally are built in areas where there's great potential for damage from those kind of scenarios. So just to be clear, in that particular example, the epicenter and the focal point, as we show here, we're actually in the Santa Cruz Mountains, about I think it's about 40, 50 miles to the so 60 miles, I guess, from San Francisco, from the south by southwest of the San Francisco Bay Area. But the key thing here is that there's damages because we didn't really plan or develop cities in the best places. Not really clear at this point there's an option, but we need to consider that. Okay, so switching gears here a little bit, I'm going to talk about how humans play a role in actually causing earthquakes. This a few years ago was considered quite a controversial topic. Nowadays, I think most people have come to recognize it occurs, but this became an issue particularly around the idea of hydrofracking and shale gas development for energy in locations, including Ohio, but certainly in Ohio, Oklahoma, and Texas. And basically, the rule of thumb here is that any time we load the crust, put more of a load on the crust, so we can do that by creating a dam and putting more water behind that dam, increasing the weight on a given area of rocks. So building a dam or reservoir. We can do that by injecting fluids into the ground subsurface, increasing the pressure in that localized area. We can do that by building a really big building, for example. That if we load the crust, we increase the likelihood of a seismic or microseismic event because of that. The one that became the most common, or the most commonly discussed, at least in the last few decades, is the disposal of waste into the subsurface environments. So we'll come back to this towards the end of the semester, but what many people don't really think about very much in terms of sustainability is what we do with all our junk and all our garbage. The topics that kind of get talked about a bit historically have been nuclear waste. There's been a lot of political controversy around nuclear waste repositories and where we're going to take our nuclear waste from various power plants and research areas and where we're going to put them. And the concepts, we'll get back to those things specific to nuclear later, are usually around the idea of injecting into the ground, putting it in deep caverns, putting it in wells. And where that became sort of a more common occurrence in people's backyards. And that's always unfortunately, the name of the game in environmental science is nobody wants it in their backyard, which again leads to a whole variety of social and environmental justice issues. But when we got to about 15 years ago, certainly from the last decade, where shale gas development started to become common, where shale gas development started to become diffuse and around a lot of areas of the US and Canada, what we realized, or what sort of evolved, is that we had to dispose of nominally 5 million or more gallons of wastewater per well. So, for example, Ohio has something like 8,000 shale gas wells. So that's a lot of water. And one of the ways people were doing this is just leaking this material into rivers and streams, just the idea being the key to the dilution is pollution, or pollution is dilution, sorry. But that wasn't really a sustainable idea. Most folks sort of got behind the idea that wasn't a good strategy for wastewater in the shale gas because of the volumes and the currents of biocides, organic chemicals, salts, and naturally occurring radioactive materials. And folks wanted to basically dispose of this by doing deep well injections. Now, you may not know this, but Ohio's activity or economic impact from shale gas development was actually the amount of money developed by wastewater disposal was comparable to the amount of economic impact from shale gas development in this area. States like Pennsylvania, West Virginia eventually started doing this, but early on they didn't actually have the permits to do wastewater injection wells. Ohio, particularly right along the border, Youngstown area of Ohio, Ohio was permitted to do this. It became a cottage industry to purchase land, drill an injection well, and basically accept wastewater from Pennsylvania, originally West Virginia. People drive it by truck or train across the border and inject that water into the subsurface in those areas. And as a result, we've learned since then that this process, and I'll take you through how, can cause earthquakes or micro seismic events, in these areas. And the third way we've come to realize that humans can cause earthquakes is actually through underground nuclear explosions. I'll take you through that later, but when we were doing seismic testing, not just the United States, but some of other nuclear powers, what they came to realize is that by dissipating that amount of energy is the same factor that can actually induce seismic events in the subsurface, through underground explosions. So again, the most clear one I want to talk to you about is wastewater disposal. There's a famous example on an Air Force, I think it's on an Air Force base here near outside of Denver. Between April 1962 and November 1965, there was a wastewater injection well injecting water in the subsurface. And in those nominally 3.5 years, there were several hundred earthquakes reported in Denver and nearby area. Some of them actually up to the sizes that were relevant in terms of inducing, shaking and impact, magnitude up to 4.3. And basically, to give you a sense here, is they are actually injecting water and waste into the subsurface pretty deeply, about 3.5 kilometers below the surface. And it was the Rocky Mountain Arsenal, which is an Air Force and base and weapons repository. And basically, is that what people started to realize after a while is that when they're actually injecting this wastewater, they're injecting it into highly fractured metamorphic rocks. And when they would do that, what happens is that fluid gets injected under relatively high pressure. It increases what's called the pore fluid pressure of those rocks. And as a result, once you increase the pore fluid pressure significantly, the rocks, which are normally sort of have friction holding together, can actually have the pore fluid pressure increases, and they can sort of slip past each other more readily. And basically what people realized after a few years is that every time they injected, they could actually make earthquakes. And when they'd stop, there were long periods of quiescence, so there was no seismic activity. So that became it was back in the 60s, became a pretty important study where people started to realize, what the impact of injecting fluids were. They started to realize how earthquakes actually worked and related to different aspects of pore fluid pressure. And although I didn't talk about this, there are a lot of micro seismic events and minor earthquakes in periods of intense rain and intense snow melt in certain areas, not usually leading to major earthquake events, but there's some aspect that are actually dictated by how much water, and even a natural process is getting loaded into an area. So, a little bit of diagram on this one. The arsenal disposal well was injecting water into this fractured metamorphic rock below these sedimentary rocks, but there was this North Denver fault here, and basically when they actually looked at the earthquakes per month and the injection rates, there's a pretty close match to the amount of injections and earthquakes. And what's important here is that once they stopped doing injections in 65, there's been almost no active seismic activity along that fault in this area at all. Closer to home, Youngstown, Ohio. This is back in the 2015 timeframe, something there. There was a relatively large number of very small earthquakes. In fact, some people would debate whether it's acceptable to call them earthquakes as opposed to microseismic events. But these were actually tied to a single fracking wastewater disposal well, which the same process, injecting water into the metamorphosed sort of core complexes beneath the sedimentary units of the geology of Ohio, actually caused 167 earthquakes in that area. There were no recorded earthquakes reported in Youngstown before 2010, but then as the wastewater was pumped about 9,200 feet at this one injection spot, within 2 weeks there was the first earthquakes felt, and most of this was sort of like controversial. Of course, as the more water is injected, the more pressure builds up, the more likely earthquakes and microseismic events are to happen. It was pretty much considered controversial to about the mid 2000s, 2015, even though we knew what we knew in the early 1960s. But eventually, people now, I think, have started to accept the fact that this can be an ongoing problem in this area. For perspective, these weren't very big earthquakes. It's debatable whether they are relevant in terms of doing damage to the area. I think the highest one ever was still below magnitude of 3. So I'm not minimizing it. I think it's an area of active concern, and certainly there can be faults that have more stress built up on them, or the magnitude could be higher. And this is actually something where along the entire Pennsylvania-Ohio border there, both in PA and Ohio, there's been a pretty big increase in seismic activity related to this injection process. The other location, of course, was actually brought up in Oklahoma, where this is commonly occurred. So this particular well, when they realized the frequency of earthquakes, 167 earthquakes, this one got shut down. This activity of wastewater disposal along wells in Ohio actually continues today. In my opinion at least, what's really happened, this is something I do a lot of work on as background, but what they've really realized is that, effectively realized is that certain wells are in areas that are more stress built up and are more likely to have earthquake events. And as a result, that well's been shut down. In areas where they're seeing a lot of seismic activity, they sort of reduce the number of permits and reduce the number of wells active in those areas, where they've expanded that activity to other locations and allowed more wells where there's not clear evidence of seismic activity. So this does continue, but is important. And here, as I'm going to talk to you about, is in Oklahoma. The scenario there is actually far more common than in Ohio, effectively, where they had a great number of earthquakes. This is in the continental interior of the United States. It's an area there's no active plate boundaries. There really is not a very, very big precedent for for seismic events, but in this area, sorry, around Oklahoma City and to the north of Oklahoma City, because of wastewater injection, there were a great number of seismic events that were eventually showed, basically developed when wastewater disposal was occurring. So, what does it matter? This applies to both natural and anthropogenically induced earthquakes, but what are the issues that we actually see when we find earthquakes? The biggest one is the R waves, which I've talked about in great extent, is the R wave shaking and ground rupture. This can often lead to extreme damage to infrastructure, pipelines, buildings, bridges, and can really can kill a lot of people, injure a lot more, and do an extreme amount of damage. The second factor I wanted to bring up here is actually something called liquefaction. And this is where I'm going to go back to those unlithified or not yet solidified rocks in terms of the alluvium and mud sediments. And what happens is those sediments can actually, if they have a high amount of water in them, when they get shaken really rapidly, they can basically liquefy. And liquefaction basically means these can actually start to flow. And as a result, you can really imagine if you have a bunch of buildings, bridges, roads, pipelines built on an area, and it starts to flow away, you can see an incredible amount of damage from liquefaction in those scenarios. This liquefaction and just the shaking together can actually lead to major landslides that can do incredible amount of damage, particularly volcanic related earthquakes, which we didn't talk about this much, but when there's magnetism, such as what's going on under Yellowstone, for example, when magma moves around, it can actually cause the ground to shake, and often these can lead to liquefaction and landslides of both montane glaciers and also alluvial sediments on mountain ranges. Largely because of the infrastructure that's tied to this, pipelines, etc. Fires are very common now in major earthquakes. You can often see that these liquefaction, shaking, which can move or offset the landforms, can actually cause groundwater in given regions to change direction of flow, elevation. So people can have water wells drilled to 100 feet. They can be accessing groundwater for the lifetime of the well, and all of a sudden, they move the water table down. All of a sudden, there's no more water in people's wells, or for example, areas that are currently lakes, land can change. Landforms can start, ruptures can change the surface, and the water can flow back out. Lakes can be drained. Others can be created, so there can be flooding tied to this. When these earthquakes are near lakes or the ocean, obviously many remember the Boxing Day earthquake back in 2005 potentially, or at least have heard about it. These can generate incredibly large earthquakes. The Fukushima tsunami, again caused by an earthquake. I think that was back in 2010 or 11. But what's often not really thought about in terms of the implications of earthquakes is actually the occurrence of various diseases. These are not necessarily as if something infectious is going to be released during an earthquake, but as a result of damage to infrastructure, particularly damage to water supplies, and actually direct pollution of sediments, chemicals, things like that into water supplies. One of the biggest implications of a major earthquake, as well as other geological hazards we'll talk about later in the semester, is the occurrence of waterborne diseases or infectious diseases, just because there's lack of infrastructure and support for those scenarios. So what I'll do here is we'll pick up. We're going to end now. We're going to pick up on this effects of earthquakes in specific towards the end of or the beginning of class on Wednesday, and then after that, when we wrap up, we'll move on to discussing volcanic hazards next. So again, hopefully everyone's recovering from the week of busyness with the exam and the worksheet last week. Next worksheet will be posted on Sunday for do a week from Friday. And again, great job on the exams. I was impressed by the scores. So we'll come back to discussing the effects of earthquakes a bit more in the lecture on Wednesday. Hopefully everyone has a great day. Talk to you soon.